Hi guys, today I'm going to show the proof of the Simpson's rule error limit, right? So, put another way, I'm going to show the proof of the error limit for Simpson's rule. Before you start this video, you should know what Simpson's rule is, and you should know this error formula here. You should already know that stuff, not where it comes from. This video, what this video is about is to show where this comes from, okay? And I didn't come up with this. I'm already saying that I'm just copying this content. I'm straight out copying, flat out copying this content from Math Easy Solutions. I think that's the name of the channel, and I think the guy's name is Matthew. So the reason I'm doing this is because he develops the proof as he goes along. So he takes 1 hour and 45 minutes to do this, and I'm hoping to do this a little bit faster since I've already written everything that I had to. Okay? And you should know this formula. Just know that this formula exists. Okay, you should know about Simpson's rule. You should know Taylor's polynomial, and you should know Lagrange's polynomial. All right. So here we have. Oh yeah, and you also have to know integration by parts before you start this video. Otherwise, you're going to be completely lost. So here we have the formula definition of Simpson's rule, okay? And so you have the integral from a to b of f of x dx, which equals the approximation Simpson's rule. That's what this st here means. And you have a total error, okay? Now, this formula is not going to give you the total error. It's just going to give you the limit of the error, okay? K right here is going to be the maximum absolute value of the fourth derivative of f of x in the domain from a to b. Okay, and there's something else too, guys, because the books try to make this very confusing. What do you call a to b? In this case, I'm saying x0 to xn, okay? Because actually, when you have a bunch of, since you're going to be working with two interval sets, so you have here and here and here and here and here and here, okay? 1, 2, 3, 4, 5, you need another one, 6. Okay, so this is x0 and this is a, all right, for the first two interval set, which is this one. Now you got an x1, which is going to be c, it's the midpoint, and you have x2, which is b, okay? And now you got a problem because you have x, this was very tight in here. Okay, I'm just going to keep going, doesn't matter. Now you have over here, I'm just going to do this because it's tight. Now you have an x3 here, which is the new a, it's the a of the, oh, as a matter of fact, hold on. Actually, x2 is going to be the a of the new two interval set. So you have a 1 2 interval set here, you got another 2 interval set here, you got another 2 interval set here. So you have a, c, b. This b is going to be the a of the next one. So x2 is b for this one, and it's a for this one. Okay, that's why it's confusing. So you have a, c, b. All right, so here you have x3, here you have x4, and x4 is going to be b for this two interval set, and it's going to be a for this two interval set. So you have a, c, b, and this b is a, c, b, and this last b is a, c, b, and it keeps going. So let me undo these things in here. All right. So when I say from a to b here, it means from x0 all the way to xn, okay? From the first point to the last point. Okay. So there's this formula here. Right, is the integral of the fourth derivative of x times px, right? The integral from a to b. This a to b here is just going to be one interval subset. So actually, this a to b here means from x0 all the way to x2. Okay, so it's going to be x0, x1, and x2. That's all. This is just for one interval, actually for a two interval set, because in Simpson's rule, you're not working with just one interval, you work with sets of two intervals at a time. So that's what this thing in here is. the error, okay? It represents the error perfectly, not the limit of the error, just represents the error. Now, where does this stuff come from? Well, when you study books whose titles are similar to numerical analysis, you're going to find a different way of deriving Simpson's rule from what is shown in a calculus book. They're going to use Lagrange's polynomial to derive, to make the Simpson's rule, okay? And there's going to be one last term in there, which is this one in here, okay? When you work with Taylor polynomial, you go like this, right? You got a polynomial here. This is going to be like Taylor polynomial, and this is going to be like f of x plus the first derivative of f of x. Well, let's just say in a case you're working around the point c, it's going to be like f of c, which is the midpoint, plus the first derivative of f of c times x minus c, okay, plus the second derivative of f of c times x minus c squared divided by 2. Okay, and plus the third derivative, I'm going to put 3 here, f of c times x minus c cubed divided by 6, because you keep doing the factorial in the denominator. Okay, so the first one is 1, the second one is 1 times 2, the third one is 1 times 2 times 3, so this is going to be divided by 6, and the fourth one is going to be this thing here. It'll be, I'm not going to write here because it's already very tight, maybe in here. It's going to be the fourth derivative, okay, of f of x, of f of c times x minus c to the fourth divided by 24, all right? So the fourth derivative is right here. And this p in here, that's what it is. It's a quartic polynomial, right? It's a polynomial whose largest power is 4. So you have x minus c to the fourth. This is going to end up being an x to the fourth plus 4x, blah, 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 right? X cubed, c squared, or could be minus because multiplying here. And you don't have the 24, right? Here's the 24. Where's the 24 in here? Down here, it's not there. But we're going to put it there, okay? We're going to create two constants, d1 and d2 along this formula. And these constants, when worked through, they're going to show up with this 24 in there. So this is what happens when you make Taylor's polynomial. And this is going to represent the error, which is going to be negligible as long as x is close to c. If x is close to c, this term in here is going to be very small, less than 1. And when you make like 0.00001 to the fourth, it's going to make it even smaller. So there's going to be a very small error, okay, around the point c. So that's where this stuff comes from. I'm going to do this as much as I can. I'm going to have to erase the rest. Okay, so that's where this comes from. It's one thing that Matthew neglected to mention. Okay, he forgot to mention this because he starts the proof with this, but he doesn't explain where this comes from. It comes from deriving Simpson's rule from I forget the thing, from Lagrange's polynomial. Okay, so here we go. So we're going to integrate by parts once. Okay, so what is px? Px is a monoquartic polynomial, means it's a polynomial of degree 4 where the largest degree coefficient is 1. So you have x to the fourth plus a3x cubed, right? Plus a2x squared. We don't know what a3 and a2 are, but this one in here has to be 1. Okay. So here we go. Yeah, there's something else too that I want to mention. This P of x in here, it's not this one here of the picture, okay? Because the P1, the P of x in this picture here has to be a parabola. So it's an equation, or well, we can call it an equation of largest degree equal to 2, not equal to 4. But this one here, the degree is equal to 4. So just to avoid confusion, this px in here is not the p here that you see in the picture. Okay, so you integrate by parts once, okay? and then you integrate by parts the second time. There's something else too. The v, because integration by parts it starts with integral of u dv. dv is always going to be the derivative of f, because you want to integrate that stuff all the way to f, okay? And the u is always going to be p, because you want to differentiate this all the way to the fourth derivative of p. Okay, so u is always going to be p, and dv is always going to be some differential, some derivative of f of x. So you integrate by parts once, you integrate by parts twice, okay? We integrate by parts the second time. So these numbers that you see in here, the 1 means that it's being integrated by parts once, and you got a 2 here, okay? And then you have a 3, and then you have a 4. So you integrate by parts 4 times. Right? There's something else too. In the end, you're going to end up with du equals the fourth derivative of p of x dx. This equals to 24 dx. How do I know that? Well, just as a recap, you guys should know this. Doesn't matter. a3x3 plus a2x squared plus a1x plus a0. Okay, so the first time you differentiate, you knock this out, and you knock this x out. And there's something else too. This becomes 4x cubed, right? This is going to become 3a cubed x squared. All right, so the second time that you differentiate, you're going to knock this a1 out. Okay, so you guys know where this is going, because you should know this by now. So you differentiate it once, you get 4x cubed. You differentiate it twice, you get 12x squared. You differentiate it 3 times, you get 24x. And if you differentiate it 4 times, you get 24. So that's how we know. Okay. All right. So we keep going, right? And here you go. Now put everything together. So this is the original equation that we started with, right? And then you're integrating this stuff from a to b. And from a to b here, this is just, it's from x0 to x2, okay? We're just worrying about one set of 2 intervals for now. Later, we're going to use summation to worry about all the sets, but for now, we're just caring about 2 intervals set. Yeah, it's kind of complicated to speak this. Okay, so put it all together, you have this, all right? Now, instead of integrating from a to b directly, I'll integrate from a to c and from c to b, because c is the midpoint here. Okay, so like I said, c is the midpoint. So this one here is actually going to become 2 terms, all right? You have p of x, the third derivative of f of x, and you have p of x, the third derivative of f of x, again, from a to c and from c to b. This one, the same thing, from a to c and from c to b, except the last one. The last one, I'm just going to keep it this way. And this is what you come up with, okay? This formula in here. Now, it's time to integrate this formula. Well, I wouldn't say integrate. Yeah, it's not integrate because it's already done. It's time to substitute. You have to put the c that's in here over here, and you have to put it here, and then you have to do minus and the a, right? Okay, so this is actually going to become 2 terms, and this is going to become 2 terms. All right, this is going to become 2 terms, 2 terms, 2 terms. All right. When you do that, when you expand all that stuff and you collect like terms, like factoring out stuff that's together, you come up with this big formula here, right? I'm just going to stop the video here for a second so you can read that thing. Pause the video. Okay. Now you have this big formula here. We're going to have to work on this to the end of the proof, okay? Now, f, this f in here, the integral of this f is what you're trying to find out what it is, okay? So you have something like this, and you have the f, right? This is the f, coming from a all the way to the final b. This is not just one set. As a matter of fact, I'm just going to say x0 to xn. So there's no confusion. All right, And now you have a p, okay? But, well, you know what? I'm just going to say x2. Because right now we're just worrying about one set, right? So it goes from x0 all the way to x2. So you have f in here, which is continuous, that's fine. But here's the thing. We want to have access to this f in here. When you expand it, okay, where did all this stuff come from? It came from expanding this. So when you expand this stuff, you're going to come up with all these terms in here. But we don't want the third derivative of f of anything, okay? So the third derivative, the second derivative, the first, we want to knock all these things out, all right? And there's some, yeah, you got it here again, you got it here again, you got it here, and you got it here. What you want is just the f's. The only thing that you care about is this term in here, because it's just an f, it's not the derivative of f. This term in here you care about, and this term you care about, and this one, of course. Okay, everything else you want it to become 0. Now, how do you do that? Well, the polynomial, you can just say that p of a and p of b are going to be 0. You can just force it. Okay, so p of a equals, as a matter of fact, I already wrote it down there. See here? P of a equals the first of p of a equals the second of p of a equals p of b equals the first of p of b equals the second of p of b equal to 0. If you do that, you're going to knock out all these terms that are underlined, right? And you see, there's something else too. We're going to knock all these things out, and then you're going to go like, okay, why does the f, this is something else that Matthew forgets to mention in his proof. Why does the f is always of c? It doesn't matter if it's the derivative or not, but when you're dealing with f, you got a c, and when you're dealing with a p, you got a c minus and a c plus. What the heck is this? Because we're not talking about limits, okay? Oh, it's c approaching from the left and c approaching from the right, but why? Because it's just p of c, right? If you have p of x, and you plug a c in here, you have p of c. It's not coming from the right or the left. It's because the p from a to c is going to be 1, and from c to b is going to be another. All right? But you want to knock out all these terms in here. If you want to knock out all these things, you want, right, the p of c in because, how can I explain this to you guys? This is x1, which is the c, okay? So you have a here, you have c, and you have b. There's going to be a function, an equation here that's going to be some kind of graph, okay, on this side. And you're going to have a graph on this side, which is the p of x in here and the p of x in here. These p of x's are not the same. But to knock out these terms, you want the left p of x, this one, to equal scalar when it's at c, okay? So this left in here, you can do p of c, and it's going to be some kind of scalar. Let's just write s. And you want the right one, this one here, which is also p of c, to equate s. You want them to be equal, because if they're equal, you can, okay, it's going to be like s in here minus s in there, which is just going to be 0, and that'll knock out that term. So that's what you want to do. You also want the first derivative of the p to the left of c be equal to the first derivative of the p to the right of c. You also want that for the second derivative, okay? So we're going to force that. Okay, so let's keep on going. All right, now to make this happen, I have to do this. Remember that p is going to be a fourth polynomial. It's going to be a monoquartic polynomial, right? Fourth degree polynomial. So if you have x minus a cubed in here, all right, times x plus d1, you're going to have a fourth degree polynomial here. And you can see that by inspection, because we're going to you see that this is a multiplication. You have a term here being multiplied by a term here. You're going to have to use the product rule for differentiation. But by inspection, when you look at this, you know that the p of a is going to be 0, because if you plug in an a here, this is going to be 0. okay, if you differentiate the stuff, it's going to be like 3x minus a squared times x plus d1 plus 1 times 3x minus a. Okay, by inspection, I'm already doing that in my head. So I know that the first derivative of p of a is also equal to 0. And the second derivative of p of a is also equal to 0, but not the third. Okay, so the third derivative of p, well, yeah, actually, no, yeah, you don't want that to be. The third derivative of p of a is going to be different than 0. And you go like, how do you know that? Because we're going to force it. And you can force it because of this d1 and the d2. We're going to force these conditions, and with these conditions, d1 and d2 are going to have the right values to make it work. Okay? So for x going from a to c, you have this thing. For x going from c to b, you have this thing here. Okay? So this p is to the left of c, up to the c, and this p right here is from the c and on to the right of c. Now px is supposed to be continuous for up to the second derivative, so that means that p of c minus equals p of c plus. So what we're going to do is we're going to get this equation and equate to this equation. All right, why do we want to do that? We want to do that, see, plug it in px, so we did that, okay? You have, oh yeah, there's something else too. I'm just getting ahead of myself in here. So if you plug in p of c minus, you're going to use this equation. So you put a c minus a, okay, and c plus d1 equals. Now you're going to use this equation because this one means p of c plus. So c minus b cubed c plus d2. All right, you want to equate these two. And there's something else too. You got to understand that from c, because c is the midpoint, you have a, right? A, c, b. From c minus a equals b minus c. Right? This minus this equals this minus this because it's the midpoint. But that also means that c minus a equals minus c minus b. And that's what you have in here. Right? Why are we doing that? Because now you can just plug in, you see, you got a c minus b here and a c minus a, but you want to transform this thing to c minus b too. So what is c minus a? Equals minus c minus b. So there you go here. Okay. Now you have this minus being cubed. It's still going to be a minus because a minus cubed is a minus. Now you see you have a c minus b cubed and a c minus b cubed here. You can just cancel them. You're not going to cancel the minus though. And what you have, this minus is acting on this c and it's acting on this d1. All right? So you have minus c minus d1 here equals c plus d2. All right? And now you are going to get 2c equals minus d minus d1. But what is c? Since it's the midpoint, it's a plus b divided by 2. And now you have d1 and d2 in terms of ab. That's one equation. All right? Now you want another equation. You see, well, what I did was just to get the... It's so hard to see this thing. Okay, so what I did is just to equate this equation to this equation so that in the end, I'm going to have d1 and d2 in terms of a and b. Now I'm going to differentiate this one and I'm going to differentiate this one and they still have to be equal. All right, at c. They still have to be equal at c. And I'm going to equate the first derivatives again so that I have another equation of d1 and d2 in terms of a and b. Why? Because I want to know what d1 is in terms of a and b, and I want to know what d2 is in terms of a and b. So we're going to make a system of two linear equations with two variables. What are the two variables? Because if you have d1, d2, b, and a, you actually have four variables. But don't worry about that. The variables are d1 and d2. Okay, it's like it's the x and y. And a and b are just scalars, whatever. As a matter of fact, they are scalars. Okay, so we're going to do it again. I'm going to differentiate the first p, okay, and this is what we're going to come up with. And similarly, we're going to do for the second p, okay, because we have two p's, one to the left of c and one to the right of c. So you differentiate it again, all right? And now remember, for p to be continuous, the first derivative of the left p has to be equals to the first derivative of the right p. So we're going to get this equation and equate to this equation. And what is that going to give us? That's going to give us a second equation in this format of d1 and d2 in terms of AB. So we do that in here, okay? I equated the stuff and I just work it out. And here you got another d2 and d1 in terms of AB, right? Now you're going to use these two formulas. You're going to use this formula, which is here, and you are going to use this formula here at the top of the screen, which is here. Okay, now we have a simple system of equations, and then you solve the system of equations for d1 and d2, and we find that d2 equals this, minus 2a minus b divided by 3, and d1 equals minus a minus 2b divided by 3. Okay, let's keep going. Now, we had the first derivative, okay? You want to do the second derivative again. Why? Why do you want to do this? You have the p of x, and they have the first derivative of p and the second derivative of p. Why do you care about this stuff? It all comes back to this big formula, okay? You want to knock this thing out, so you have to know what this equals to. You want to knock this thing out, you want to knock this thing out, all right? And you just want to keep this one. So we need all these derivatives of p. So here we go again, all right? We have the second derivative. I don't know if I already got to the system of equations. Yeah, I got to the system of equations, fine. All right. And now I differentiate it again. So here is P2. What's the final formula of P2? It's this one. Okay. And you have to plug in the D1 because this P2 depends on D1. But now we know what D1 is. It's minus A minus 2B divided by 3. So you plug that in here. Okay, so after plugging it in, you have this thing. You can see that now it's 4 times x minus a times 3x minus 2a minus b. d1 doesn't even show up in here anymore. Okay, you're going to do the similar thing for the other part. So you have the second derivative of p of x, which depends on d2, and you're going to plug in the previous value of d2 that you found, okay, which was here. Minus 2a minus b divided by 3. So you're going to plug that in here and you're going to come up with this formula. Alright? Okay. And now, let me see here. And now you have you want to apply the c, right? Now apply the c value for x on the second derivative formula for both the intervals from a to b and from c to b. From A to C and from C to B. Okay, so this is the second derivative of the p of x to the left of c. Okay, plugging the c in here and in here, you got to remember that c is a plus b divided by 2. So you plug that in here and you're just going to come up with a small formula. Okay, so what is this? This equals to the p, the second derivative, right, to the p of x to the left of c. That's what this b minus a squared equals to. Okay, you're going to do the same thing for the p of x to the right of c. Okay, so you have this thing here, you plugged in the c, you replace the c for a plus b divided by 2, and you got this. Look at that. Okay, you can see that this are equal now. Now it's proof. Why? Because b minus a squared and a minus b squared, because it's squared, it's always going to be positive. Okay, so therefore it's proven that the second derivative of p of c minus equals the second derivative of p of c plus. We have proof of that now. Now I'll work on a third derivative. Why? Because we need it, right? Remember the big formula here? We need the third derivative over here. So, here we go. I'll work on the third derivative. So you get the third derivative, okay, on the left of c, and you get the third derivative on the right of c. This is the third derivative on the left of c, and this is the third derivative on the right of c. And now you see, okay, so now you have p of c, you have the first derivative of p, the second, and the third. Okay, what do you care for the third derivative of c? For the third derivative of p, you care about the c minus and the c plus. Okay, because you also want this f of a, you care about the a and you care about the b. So you're going to have to put a, b, c minus, and c plus in this third derivative of p. Okay? Because, recapping, you want to knock these things out. You want to knock this out, knock this out, knock this out. You just care about these four terms in here. Why? Because that's where f of c shows up. Okay? That's where f of x shows up. That's why you care. You don't care about its derivatives. So let's go back down there. And work on the third derivative. Okay. And get this. After you work on the third derivative, you plug in the values of a and c minus in this one. You're not going to plug in the values of c plus or b in this formula. Why? Because this is for, the values of a and c minus, you're going to plug it in this formula here. Why? Because it's from a to c. Okay? Now this one is from c to b, so this is going to be for c plus and b. So after you substitute all these values, so a is going to go on this formula, c minus is going to go on this formula, c plus will be on this formula, and b will also be on this formula. After you do that, you're going to get these values. See, minus 4 divided by b minus a, minus 4 times b minus a, 8 times b minus a, minus 8 times b minus a, and 4 times b minus a. So you know that there's a very close relationship to all these things, okay, to the third derivative of p, both on the left and the right side of c, and things are just a multiple of one another, okay? Okay, so let me see here. Let's keep on going, all right? Now getting back to the huge equation of integration where all the zeros have been removed and accounting for the new relations, I have this. So this thing here that you see, okay, is just this formula, the big one. Where is it? It's this formula with all those things knocked out, okay? It's just this stuff in here that you care about. Everything else, you don't care. So, here we go. Okay, so these are the terms that you care about. You see F, 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 and F. You don't have the first or second or third derivatives of F in here. Now plug in the values that were found for the third derivatives. What does that mean? Well, for example, here you have an f of a. What is the third derivative of p of a? Okay, it's minus 4 times b minus a. That's what we got here, right? Minus 4 times b minus a for the third derivative of a. So you just plug in these values. Okay? From here to here, you're just plugging in the values. Here, you see that this is going to be in, let me think here, the third derivative of p of c minus, what is it? It's 8 times b minus a minus 8 times b minus a, right? Because this, we're going to plug it in here. So it's going to be 16, right? The whole thing is going to be this is going to be 16b minus a, but because of this minus, it'll be minus 16b minus a. So that's what you have in here, minus 16b minus a, and you keep plugging in the things, all right? Now, after you have this, there's a minus here, okay guys? After you have this equation here, this equation, you're gonna factor out the minus 4 times b minus a. Why? Because this has the same format as Simpson's rules. You see, you just came up with a big term in here, which is f of a plus 4f of c plus f of b. This is Simpson's rule. This is the approximation that we want, okay? So this shows that we're going on the right track. Now, when you divide everything by 24, so you're going to divide this term by 24, you're going to divide this term by 24, divide this term by 24, okay? Yeah, you do that. And you're going to pass, okay, this is on the left side of the equal, this is on the right side of the equal, this is on the right side of the equal. So you're going to pass this thing here, this one to the left side of the equal, and this minus is going to become a plus. Okay, so this is what you have in here. Look, the integral of a, from a to b of f of x dx is equal to the Simpson's rule approximation, which is this thing, okay, plus this stuff in here, which is the error formula. Remember that I said that we started out with this formula here without the 1 divided by 24, but as you worked it out, the 124 was going to show up from the values of d1 and d2. Okay, so this is the error that we care about. This is what we're trying to find out. Okay, but here's the thing. Well, let me see if it's already time to do this. I don't know if it's already time to talk about this thing. Okay. Here I'm just saying that p of x, okay, is x minus a cubed, x plus d1, but now we have the value of d1, so I just plugged it in here, all right? And the same thing for the p of x to the right of c, which is this one. Okay, now consider k to be the highest absolute value of the fourth derivative of f of x in the a to b domain. Since we're still working on the, how can I explain this? Well, for this, so far everything that we've done is just for a 1-2 interval set, okay? But at this part of the formula, when I say from a to b domain, it's the whole thing. It's from x0 all the way to xn, okay? Why? Because you gotta work with this thing, right? Now you have an x in here in this polynomial, and you also have an x in here in this equation. This is never gonna end. Okay, you're going to be integrating by parts forever. This is never going to end. So in order to make this end, you want to knock out this fourth derivative of f of x in here. You're just going to consider this thing k, okay, which is the maximum absolute value of the fourth derivative of f of x all the way from x0 to xn, right? So now you don't have to worry about an x in this term because this term is just k, okay? So that's what I did in here. See, the total error equals the absolute, because the total error is an absolute value, it's the absolute value of this thing, okay? The error equals this because so far you have the exact fourth derivative of f of x. But now when you replace this fourth derivative by the largest fourth derivative, which is k, this term in here becomes greater than or equal this term. Okay? All right. So k divided by 24, and you still have to put the p of x in absolute value because p of x, the integral from p of x might be a negative area, okay, in some instances. So what is this going to be from a to b? It's going to be, yeah, there's something else too. You have two p of x's. You have a p of x to the left of c, and you have a p of x to the right of c. So how do you integrate this from a to b? Well, you integrate from a to c with the first p of x, and you integrate from c to b with the second p of x. Okay? Now the next step is to get rid of the absolute value operator, because you see you have the integral, right, of the absolute value in here, and you want to make that go away. So the x minus 3 cubed is always greater than or equal to 0, of course, because a is the first point. So when x equals a, this is going to be 0. If x is anything greater than a, this is going to be positive, so you don't have to worry about that. Okay. On the other hand, the 3x minus a minus 2b divided by 3, this term is always negative, no matter if c or a is plugged in. Okay. So just plug it in, put an a here, and you're going to see that it's true. Or put a c in here, and then you have to replace the c for a plus b divided by 2. Now, after you do that, I didn't do it in here, but I mean, I did it and I erased and I just made this note, okay? So on the other hand, this term is always negative, no matter if c, blah, 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 blah. Remember that c equals a plus b divided by 2. Therefore, flip the signs of this equation. So you see, you have a 3 of x in here, it becomes a minus 3 of x in here. You got a minus a, it becomes a plus a. You have a minus 2b, it becomes a plus 2b. All right? Okay, and do the same analogy for the second integral, for this integral here, okay? On the second integral, I replaced c in here on this x, and I replaced b in here on this x too. And I discovered by inspection that it's always going to be positive, so you don't have to flip the signs. On the other hand, x minus b is always going to be less than or equal to 0. Because x minus b, when x equals b, this is going to be 0. But b is the last point of the current interval of the current set, or the last point at all of the entire domain. If x is anything less than b, this is going to be negative. So you have to flip the signs, okay? Instead of being x minus b, you got a b minus x. Okay, so now you got rid of the absolute value operator. Now here's the thing, consider x to be a plus b minus t for the second derivative to show these two integrals are the same. All right, so what was the guy thinking when he did this? So t equals a plus b minus x over here, okay, and dx is going to be equals to minus dt. All you got to do is to differentiate these things and you'll see that that's true. Okay, and blah blah blah. Why did the guy do this for the second derivative, just for this one? Okay, this one's still gonna be with respect to t, with respect to x, but this one's gonna be with respect to t. Why? Because this thing is going from a to c and this one's going from c to b, but he wants to unite these two. So he wants the limits of the integration to be the same, right? Now, when you plug a c, this c here, on this x, okay, you have a plus b minus a plus b divided by 2. So it's like having 1 minus half. What are you going to have? Half. Okay, so it's a plus b divided by 2, which is what? C. So when x is c, t is also going to be c, so the c remains in here, okay? Now when x is b, if you put a minus b, well, if you put a b here, it's going to be a plus b minus b, the b is going to be knocked out. So when x is b, t is going to be a, all right? And now you have the same limits of integration. You have ac in here, and you have ac in here, but it's flipped out. In order to make this from a to c in here and from a to c in here, all you got to do is to switch the limits of integration and make this negative sign becomes a positive thing. And that's what we did over here. Okay? See, that's negative here, and now it's positive here. Okay? And the limits of integration are switched. Here's from c to a, and here's from a to c. Okay, everything else is the same. Now, I know that this is going to look confusing because it was confusing to me the first time. You can unite these two integrals. You can just knock this one out, multiply this one by 2, which you simplify, and you make this become a 12. Why can you do that? I was like, but why? Because t is a function of c, so it's a function of x. So you're gonna have to replace this t with an x. How do you know that this equals this stuff? Because you're changing the variable in the equation, and you're also changing the variable of integration. When you do that, it's the same stuff. Okay, look at this. X minus a, t minus a, cubed, right? Minus 3x minus t, minus 3t, plus a plus 2b plus a plus 2b divided by 3 dx dt. So you just replace the x with the t. When you do that, even though t is a function of x, when you do that, it's going to be the same area, okay? And this is going to look confusing, but I'm gonna try to prove this in here. Look at this. The integral from 0 to 1 of x dx. And now we're gonna do the integral from 0 to 1 of y dy. Okay? Doesn't matter if y is a function of x. This is gonna be x squared divided by 2. This one's gonna be y squared divided by 2. So when you plug in a 1 here and then a 0 here, it's the same as plugging a 1 here and a 0 here. Okay, so that's why you can unite those two integrals. As a matter of fact, you can multiply the first one by 2 and just disappear with the second one. And this is what's being done. Blah, blah, blah. Let me see here. This is what was done here, okay? From this step to this step. I made this one disappear. This one doesn't exist anymore. And this one was multiplied by 2. Simplifying, it becomes a 12, which is here. All right? Okay. So, you still have the left side of the equal, right? Which is this thing here. Equals this stuff. Okay. Now, do whatever I have to do to transform the underlying part into something plus or minus x minus a. So you want x minus a, or you want minus x plus a. Why? Because you have an x minus a in here, and you want to have somewhere around here an x minus a too. Okay, so you already have, look, minus 3x divided by 3. This is minus x. So all you got to do, you have a minus x, so you got to add an a. And you go to like, oh, okay, but hold on, there's already an a here. Yeah, but this a is divided by 3. This is actually plus a divided by 3. No, you want an a, okay? So, you see, I made the scam here. From this part, you go to this part, and then you go to this part. So, I copy this thing, okay? Minus 3x divided by 3 is minus x. And then you go plus a plus 2b divided by 3. And now I'm adding the a. So now I have minus x plus a, which is the same thing as minus x minus a. Alright? Since I added an a, I have to take an a away. So I made minus 3a divided by 3. Right? Why? Because I want to say minus 3a plus a to become minus 2a, all right? If you were like this, guys, minus a, I can't mess this a with this a because the denominator here would be 1 and the denominator here is 3. So I'm just taking the minimum common denominator, okay? So after rearranging the terms in here, this is what I get. So now from here to here, what I did was, you got the integral, right? K divided by 12, integral from a to c, x minus a cubed, x minus a cubed. Instead of putting this, you put this thing in here. Because it's the same stuff. So that's what I put, I copied it in here, right? Okay. And this whole thing, so we're not going to lose track, this whole thing here, okay, is less than or equal to the total, error, okay, which is being represented right now by this thing here. Okay, so we're almost getting close to the end, guys. Okay, so now you have this thing here, okay, and you can integrate it. Well, before integrating, I actually multiplied it out, okay. I have this x minus a cubed, and I multiplied it here, and then you have a minus here, and I multiplied it again by this term. So it's just a distribution property, right? A times b plus c is a times b plus a times c. So that's what I did in this step here, okay? I just multiplied the whole thing out up to this equal. After this equal, I actually integrated it, all right? Now, let me just see here one thing. Why does the k times b minus a divided by 18 was out of the integral? Because I'm integrating with respect to x, and there's no x in here. So as far as x is concerned, this is a constant. You can just move it out of the integral. Okay, so I did all this. I did all this in here, okay, which is equal to this part. All right, and now all you gotta do is to plug in the c where the x is, right? So you're gonna plug in a c here, and then do you have to plug in an a? No, because this is x minus a. If you plug in an a, it's just gonna become 0. And the same thing over here, okay? So all you gotta do is to plug the c here, and you gotta plug the c in here. And that's what I did in the next one, the next step. So putting the c and plugging in the fact that c equals a plus b divided by 2, now it's time to replace the a plus b divided by 2. You rearrange the terms, you do all the additions, subtractions, multiplications, divisions, right, blah, 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 and you end up with this, which is k b minus a to the 5th divided by 2,880. This, okay, error for one couple of intervals. So this is just for a 1-2 interval set. Now it's time to use the summation, to use the composite formula, okay, which uses the summation symbol. Now I went back to this thing in here. Why? What was the last time that we saw this thing? K12, blah, blah, blah. Okay. You see here, K12, the integral x minus a cubed minus 3x plus a plus 2b divided by 3. Well, try to memorize that formula. Okay, so you get the same thing in here, K12, integral from a to c, x minus a cubed minus 3x plus a plus 2b divided by 3. Okay, this is just for one set. This formula is analogous to the one below. Yes, because the one below is going to be in composite form, in summation form. Okay, so this equals this. But the thing is that this thing in here is accounting for everything. It's going to get the first 2 interval set, the second 2 interval set, the third 2 interval set, all the way to the end. Okay, because we're going to have to sum these things up. Right? So the K12, you put it in here, and now you want to make an, you don't want to just have one integral, okay? You want to have the integrals, because you see this a here, guys, is x0, and this c is x1, and that's it. What about x2, and x3, and x4, and x5, and x6? So that's why I'm doing this stuff in here. Now you see, this is small, so I'm gonna read these things out for you. This is the integral of x from x sub 2i minus 2 to x sub 2i minus 1. So when I is 1, this thing here is gonna be 0, this one is gonna be 1, okay? When I is 2, this one is gonna be 2, and this one is gonna be 3. So you can see that it's the same thing in here, but for all sets of 2 intervals, okay? And now you have x minus a cubed, right? That's what this means in here, x minus a cubed. Because this a is just x0, but you gotta remember, x0, it's the a for the first set. x2 is the a for the second set. x4 is the a for the third set. You have a bunch of a's, you have a bunch of c's, and you have a bunch of b's. Okay, so x minus a. So you see here that when I is equal to 1, this is going to be 0. Then this thing, when I is equal to 2, this is going to be 2. When I is equal to 3, this is going to be 4. Okay, so you have x minus a in summation form here. And you do the same thing, minus 3x, okay, divided by 3, which is this term. A divided by 3, this a is just for the first subinterval, well, it's just for the first set. This a right here is for everything, and this is going to be the c, okay? So, hold on, no, this is going to be the b, okay, because it's plus 2b, so you got 2, and you got a b here. The b is going to be x sub 2i, right? Why? Because what is the b? Again, it's going to be x2 and x4 and x6, right? You got to remember, guys, that the b of the previous integral, of the previous set, is the a of the next set. And the b of this next set is going to be the a of the set following it. So x2 is a and b at the same time. x4 is a and b at the same time. It's confusing, but once you visualize that thing in your mind, it's just going to work. Okay. Okay. So let's keep going. Now I'll replace the x that's showing here, okay, for t. But this t here isn't the one that was used in a proof previously. Remember that we had to use a t here someplace to unite the both integrals. You have a t here, you got the t. Well, this t is a new t, okay? So, here we go. Where is it, man? It's almost standing. Yeah, this is a new t, a new substitution. Why? Because you're integrating this from x to I minus 1, and the lower one is 2i minus 2. I want to transform this stuff into 0, okay? And you gotta know one thing too. If you have x 2i minus 2, and the next one is x2i minus 1. So it's just one interval ahead, okay? So what is going to be this one interval ahead? It's going to be xn minus xa divided by n. Divided by n. This equals x2i minus 1 minus x2i minus 2. Right? This x in here is to the left of this x. And how much to the left? Well, one interval, not one set. One interval, because the set is of two intervals. So you have one interval, that's the distance in here, okay? This is one interval. And this is just, we're going to call delta x. Okay? All right. So, So the t is going to be x minus x sub 2i minus 2. dt is going to be equal to dx. And now you isolate for the x, all right? So you can substitute. So you substitute this x in here for this t, for everything, right? This x in here and this x in here for this t, and this dx for this dt. And this formula here becomes this formula here. Okay? So now, I'm gonna keep going. So, when you substitute x2i minus 2 in here, t is gonna be 0, and that's why the integration from 0 is 0 here. Okay, the next one is just gonna be one delta x ahead, so I put the delta x in here. Right? Everything else is the same. See, et, less than or equal, k divided by 12, summation of I from 1 to n divided by 2, summation of y from... So you're just changing the limits of integration. Okay? And you have t cubed. Why? Because when x is what is x? Is t minus plus this thing, okay? X sub 2i minus 2. So when you plug x sub 2i minus 2 in here, minus x sub 2i minus 2, you get a 0. And 0 being multiplied everything doesn't matter, okay? But this x you have, oh, I'm sorry guys, I'm sorry, I'm making a confusion here. I'm gonna replace this x for t plus x 2i minus 2, and now you have minus x 2i minus 2. So this one cuts with that, and you're left with a t. That's why this thing cubed became just t cubed. Okay. And now you have this, all you gotta do is to copy, okay, this thing here is just a copy of this. And minus x, what is minus x? Is minus t minus x sub 2i plus minus 2. So I put this in here, right? But I wanna add all these things together, so I had to put a 3 in here, and that's where this 3 is coming from. And if you put a 3 in here, you got to put a 3 in here. Okay, so you're going to add all these things together. Okay, now let's see here. This confusing stuff. Up to this point, everything is being copied over here. Okay, you have a t cubed. And now you have x 2i minus 2. I'm sorry. Because I added this, right? Have a minus 3 x 2i minus 2, and you got an x minus x 2i minus 2, so this is going to be a minus 2 x 2i minus 2, right? Yeah, minus, and I'm gonna, yeah, it's minus 2 x 2i minus 2 plus 2x 2i. So what you're going to do is, after you work out all these things, just sum all the like terms and factor out the 2. You have x2i minus x2i minus 2. So let's just say that I is 4, okay? Let's just say that I is 2. 2i is going to be 4. And the x previous is going to be 2. So here you have an x sub 2, and here you have an x sub 4. What do you have here in the middle? X sub 3. So you have one interval, two intervals. So you have 2 delta x's. That's where the 2 delta x comes in here. Okay, now you have 2 times 2 delta x is going to become 4 delta x. Okay, divided by 3, divided by 3. And I'm just copying everything else. All right. And now from here, we go all the way to here, copying the stuff. Now, what I'm going to do is to multiply, right? You got a t cubed. I'm going to multiply here, and then I'm going to multiply in here. I'm going to distribute this t. I'm going to distribute this t. So this is what you get, all right? And then you keep, now it's time to integrate. Now I integrated. So you have K12, the summation, and you integrate this, okay, with respect to t. So you have this thing here, right? Blah, blah, blah. There you go. Now this here's an interesting thing. This part has to be integrated. This one is already integrated, okay? Now, what did I do? The K12 is here, okay? Where did this n divided by 2 come from? Well, you see, do you see an I here? This is a summation, right? Do you see an I here anywhere? Look at that. There's no I. So as long as the summation is concerned, this is a constant. And when you have the summation, for example, from I equal to 1 to I equal to P of a constant, this equals PC. So you get this thing and you multiply by the constant, all right? And That's what's happening here. You have K12 and you have this n divided by 2, n divided by 2 is in here, multiplied by this thing, okay? Yeah. Not only I multiplied it, I also already substituted from here to here, I already substituted the values. Now, when you plug 0 in here and in here, the whole thing is 0, so don't worry about it. Just plug in the delta x, okay? So you get delta x to the 4th times delta x to the 5. Okay? So you do this in here, almost over, guys. And there you go. You're going to have k and 12 times 2, 24, right? And you take the minimum common denominator, this thing here becomes 2 delta x. But what is delta x to the 5th? Delta x is b minus a. Now, here we go. Yeah, delta x to the 5th. Well, yeah, you can say b minus a. Okay. This b minus a is going to be x. Well, you see, if it's this b minus a here is a little bit different. Okay, I guess I can explain this to you guys. Delta x to the 5th equals, how do you find the delta x? It's x to the n minus x0 divided by n, right? It's the very last point minus the very first point divided by n. This is the, yeah, to the 5th, okay? All right, so that's what I wrote in here. This b minus a is xn minus x0. It's not x2 minus x0. Because you have a bunch of b's. Remember, you have a bunch of b's and a bunch of a's. Well, this a is x0, is the very first point, and this b is xn, is the very last point. Okay, so you got that and so on. So this is going to be b minus a to the 5th, which you got here, the k, which you have in here. 24 times 15 divided by 2 is going to be 180, which you have in here. And here you have n to the 5th, right? But you're going to simplify the n to the 5th with this one, and the whole thing is going to become n to the 4th, and it's in here. So there you go, guys. That's how the formula comes to. And I'm going to put in the description of this video, the original video description that came up with this, okay? The guy's name is Matthew, and his channel is Math Easy Solutions, Easy Math Solutions. I think it's Math Easy Solutions. And because his name is Matthew, right? So Math Easy Solutions. He came up with this stuff, and it's very interesting. And I'm just copying it down here. I'm just copying his content and spreading the word, because I think it's important to do this. You almost don't find anything like, for example, where does this formula come from? It's hard to find out, okay? Even if you put it on Google, like where this formula comes from, Math Easy Solutions, the only guy that came up with this that I know of. I don't even know if there's a book that shows all these steps, all these things, okay? So I think it's interesting to know.